All right, hello and welcome everyone. We're looking a little bright. Let me turn that down a little bit. There we go. So today I'm going to be doing the beginning of my lecture on the pros and cons of lattice structures. So I want to have audience participation, so we'll wait a few minutes before we get started here. Looks like I have 0 viewers right now, but hopefully that'll pick up a little bit in the coming moments here. But yeah, basically, hey, one Missel to Sarah. Yes, we're finally getting some people in here. So basically, I'm gonna tell you about like lattice structures. That's like this kind of thing where you 3D print, instead of making a solid object, you just fill it in with like some kind of hollow, lightweight structure. And I want to give you a really good theoretical understanding of why you do this and, why 3D printing has really enabled this technology. So, all right, cool. We got a bunch of people in here. It looks like my view counter isn't working right now, but we've definitely got some people joining in the chat. So I'll just go ahead and get started here. This is kind of going to be an interactive thing where I'm just going through and building up my slideshow here, and as I go through it and tell you what's going on, you'll just kind of learn as we go. Let me make sure. Shoot, my it's my mic check. I think my mic's working, but my keyboard isn't. I guess I'll just have to use my laptop keyboard. That's fine. So yeah, we're going to talk about the pros and cons of lattices, and over the course of this lecture, we'll go over all sorts of different stuff, but we'll see how far we can get today. I don't know if I'm going to do the full 24 hours in one session, but if you guys really want that, we might be able to do it. I'll just have to take a small break to go buy a 12-pack of Red Bulls. Why are we talking about such a random topic? That's a great question. So I recently did a video about these 3D printed shoes. And in that video, I said I could give you a 24-hour lecture on the pros and cons of lattice structures, just because I feel like I could. And that's what we're doing here today, because a lot of people in the comments egged me on, and they were like, yeah, I want to hear about that. Sounds boring, but actually, I hope you guys will find it's pretty exciting. So let me give you kind of a fundamental overview of what lattice structures are and why they're used in 3D printing or in engineering in general. So a lattice structure is like what you can see here. Instead of having a solid block of material, we just print out essentially like little trussed structures. If you've ever seen like a crane or a bridge, you'll often see that it's made out of individual beams that are assembled together into kind of a structure like this. But in these lattice patterns, usually it's a repeating pattern, and they're doing that just to kind of fill up an interior volume with something. It doesn't have to be anything strong, just some sort of material there. And the most common application for it in 3D printing is infill. So you'll see, like, infill looks pretty interesting, and there's a reason for that. There's a reason why we use infill. It's just to kind of fill up a volume of space using a minimum amount of material. Now, I'm going to go over, we'll start with 1 dimensions, 2 dimensions, then we'll work our way up to 3 dimensions. Maybe we'll get to 4 dimensions if we've got enough time here. So if we look at a 1-dimensional structure, this is my jump rope. Oh, hold on. Let me make this screen a little bigger so you can see. Okay, so this jump rope is essentially a 1-dimensional structure. The only thing that describes its size is its length. So there's only one important dimension here. And let's say we wanted to make a swing set. So, something that you can sit in, and you sit and you swing back and forth, on the playground. So swing set situation. If you wanted to size the cables for that swing set, basically the length of that cable is predetermined based on the size of the swing set and your installation. But if you want to change the strength of that cable, the only thing you can really modify is the diameter of this cable that's, carrying that load. So if you want to make this cable lighter and less expensive and use less material, you're going to want to make it as thin as possible. So first you'll design the overall structure, and then you'll pick out a cable that's as thin as necessary to carry the load, but it's not like overly thick, because then you're adding extra cost and weight. So for one-dimensional structures, if you want to make it smaller or lighter, you just shrink the diameter. Now let's start thinking about two-dimensional structures. So here I have a cutting board. As you can see, it's well used. If you have a two-dimensional structure like this, and let's say it has to be a certain size to cover your countertop or give you enough space to work with or something. If you want to make this stronger or lighter, you're going to be modifying the thickness here. So just like our one-dimensional structure here, if we want to change the weight and strength of it, we can just change the diameter. With our two-dimensional structure, we can change its strength by changing its thickness. So if we want it to be stronger, we can just increase the thickness. If we want it to be cheaper and lighter, we can just decrease the thickness. And the important dimensions of this thing will remain the same. So let's say it has to be a certain size in this view, but if we make it thicker or thinner, that's not really going to change the functional properties of this device. But things get a little more complicated when we get up into 3 dimensions. So let's say I have a 3-dimensional object. Let me just grab something here. All right, let's say this is our 3-dimensional object. We've got a hammer. And let's say we wanted to make this smaller and lighter, but made out of the same materials. If we shrank the diameter of this handle, that would change the ergonomics. Like, it wouldn't be the same shape anymore. It would, you wouldn't be able to grab it the same way. If we wanted to shrink the hammer head, I guess you could make it smaller, but no matter what dimension you make it smaller, and that's changing the overall shape and function of this part. Yeah, this gives me physics class PTSD. Sorry about that. But instead of removing material by making it thinner or decreasing the diameter, we can remove material by adding a bunch of holes to it. So think about lattice structures as a way to reduce the volume and mass and material required to build something while maintaining the same exterior dimensions. So these are like the functionally important dimensions of the part. You can just toss this into a CAD program that can do lattices, and you can just remove a bunch of material all throughout this piece in order to meet your strength and weight requirements. I don't know if that made a whole lot more sense in my head, but yeah, I thought it was kind of an interesting way to think about one-dimensional structures. You change the weight by just changing the diameter or the thickness of the cable. Two-dimensional structures, you can change the strength and weight by just changing the thickness of the material. And then when you get to 3 dimensions, it's like, how do you change the size or strength or weight of this without actually like carving material out of it or making it hollow or something? I think the most equivalent way to lighten a 3-dimensional object is to convert it into a lattice. It's kind of similar. Yeah, we'll get into some more stuff, but let's go to the introduction. So yes, applications sneak peek. I actually haven't built this. Oh, hold on. All right, so I actually haven't made my slideshow yet. I was gonna build it as we go along here. And I just want this to be somewhat interactive, so if you have any questions, just pop them in the comments section, and then we'll see if we can address them. So the first application that I wanted to talk about, I think I already brought it up, is 3D printer infill. So if you have any slicer program, I'll open up Prusa Slicer here. Hey King Sidorak, welcome to the chat. So if we have Prusa slicer here, I can insert a box. We'll just scale this box up. And then when we slice this, let's see. I've got weird settings going on here. Let me try and get this set up to a somewhat normal printer profile. Ender 3S1, normal. Okay, when we slice our 3D model, instead of printing a solid block of material, it adds this structure on the inside. I call this a lattice. I mean, I consider anything that kind of reduces the volume of material used inside of a part to be a lattice structure. But there's other infill types that we can use, and we can actually get rid of these external layers so we can see what's going on just with the infill. So we just got rid of all of those pesky external layers. Now we can just take a look at this, what is essentially a lattice structure here. So this is a pretty simple one. This is a two-dimensional grid just extruded up into space. So yeah. Yep, people dared me to make the 24-hour video, so here we go. Now the grid pattern is kind of boring, but let's switch it over to 3D honeycomb. And here you can see there's another pattern. I should actually shrink that, shrink this box down. I'll make the patterns a little more visible here. But yeah, it's just, instead of having to build a solid block of material, we can just fill it in with this sparse structure. Probably everyone's favorite pattern has got to be gyroid. So this is a special type of lattice structure. And I mean, I think people inherently know that there's something special about this structure compared to the other ones. And this one's much more mathematically defined, using like sines and cosines and stuff. And this belongs to a special class of lattices called, let's see, I have it in my notes here. Called TPMS, so triply periodic minimal surfaces. So there's actually a bunch of these, and I'd like to see more of them implemented into our slicers, but for now we just have gyroid. All right, and I'll get into some of the companies that are really focused on this problem. One of them is Ntopt, which I'll leave links to in the description. Probably have to, well, I'll just paste it into the comments right now if you want to check out this site. So Ntopt is one of the leading companies that's building software to be able to design lattice structures. But let's get back into this. So yeah, 3D printer infill is one of the main applications. Let's also look at heat exchangers. And while I'm doing this, I'm going to paste some of these like screenshots into the lecture so that we can kind of fill that out as we're going along here. So 3D printer infill. Now let's look up some, I'm going to do this in another window just because of the nature of Google. We're going to look up 3D printed heat exchangers. Yeah, that looks pretty good. Let's just look that up here. So 3D printed heat exchangers. Here you can see an example of one of them. They're using an external lattice to build up some material on the outside to just stiffen up this outer wall. But also on the inside, there's a bunch of interesting patterns going on. And this is another interesting application of lattice structures. And the reason they're used is you can create really large surface area using these lattice structures. So yeah, that's why we'll see them there. I'm not sure which one of these I can plop into my my slideshow here. We'll just get the one from 3D Systems and we'll cite our sources. So yeah, you've basically got a ton of surface area, and if you know anything about heat exchangers, the performance is basically proportional to the surface area. The more surface area you have, the faster you can transfer heat. That's why any type of heat exchanger or heat sink will have a bunch of fins to increase the surface area. Aerospace, you see a lot of this stuff being used in like satellites and stuff, 3D printed, 3D printed things, whether that's structural or things to handle like fuel or rocket nozzles or all sorts of stuff. You'll see it in aerospace. And also in art, so these structures are kind of pretty, and just like my shoe, you don't really need these kind of structures in a shoe. You can get something that's relatively equivalent just out of a foam, which itself is kind of a lattice structure. We can talk about that. So yeah, foams are basically like a naturally generated lattice structure. Any type of foam has a bunch of bubbles on the inside. Usually, you mix some kind of resin or plastic with something that foams, either from heating it up or some kind of chemical reaction. It'll foam up, and then that introduces a bunch of little bubbles into a part. And you can have an open cell foam or a closed cell foam. Those will have different properties, but that's like a naturally generated lattice structure. Also, you'll see it in like let me find some more lattice structures here to toss into my slideshow. Let's see if we've got... Oh, okay. Interestingly enough, when I Google lattice structures, it brings up these crystal diagrams, which are kind of like at the atomic scale, things are assembled into lattice structures. But I don't think we're going to go that far, but there are a lot of analogies there. So yeah, also, you can see them in art and architecture, and also in sports. This is something that's been making the rounds on social media. I'll just copy this into paste that. A lot of people are 3D printing this basketball that's made out of this lattice structure. I'm gonna grab this. We'll cite our sources. This model is from Muzo 3D. I don't know how he built this thing, but that's interesting enough. Paste. I'm just citing all my sources here as we're going, just to make things a little bit easier later on. Okay, yeah, so you can see these lattice structures in like these airless basketballs. Also in safety equipment like helmets, a lot of them are incorporating little lattice structures in there. And that's just to help absorb impacts. So there's all sorts of applications for this stuff. And we'll do a deep dive into that. But first, I want to answer the question, what are lattices? So a lattice is essentially any repeating structure that is composed of a bunch of small beam elements connected together. And actually, N-Topology has a really good article on this, which I'll link here. I'll just drop the link in this slideshow because I like it. And they have a great overview of different lattice structures. So let's see if I can, let me zoom in on this a little bit. I'll allow all the cookies. Okay, let me get caught up on comments here. Don't want to leave you guys behind in the comment zone. All right, Star Guy, thanks for the 5 buckaroonies. I'm taking a sick day and wanted to print the shoe, but I haven't seen your video. Anywhere I can get the file? I would just try searching for 3D printed shoe. I don't know if... I don't have the file for that one. That was something that Creality just sent to me unannounced, and I was like, okay, I guess I'll check it out. So yeah, pretty cool stuff. It's made out of a relatively flexible plastic. It's starting to fall apart a little bit, so yeah, I've been wearing these around quite a bit, and there's already parts that are coming loose, but what can you say? Yeah, I don't think Creality actually made the shoe. I assume that they contracted with someone else and just had them build it and then put their logo on there. Okay, I'll buy the P1S and I'll buy you the AMS. I have a P1P and an AMS, but I just don't use them really. Okay, 24 hours, and you just started 13 minutes ago. So, Nathan, what are you 3D printing? I'm not going to 3D print anything. I don't like 3D printers, if you don't know. Yeah, heat exchangers are cool. Is the NBA printed ball everyone's been talking about a lattice itself? Yeah, I would describe that as a lattice. So, back to my analogy of like 2D versus 3D objects and how you can change their weight. For something that's two-dimensional, you can make it lighter by making it thinner, but you can also make it lighter by adding holes to it. So, like any kind of expanded mesh, I'll Google some expanded mesh. So this kind of stuff, it's or like perforated sheet metal like this. This is another way to make things lighter. So you can either make things lighter by making it thinner or by adding holes. With a cable like this, you can't really add holes to it. You can just make it thinner. With two-dimensional stuff, you can make it thinner or add holes to it. With three-dimensional stuff, you can't make it thinner, otherwise you're changing the functional shape of it. But you can add holes to it to make it lighter, and that's what you're kind of doing with lattice structures. It's Creality, so of course it's falling apart. Yes. Yeah. That's some low-hanging fruit of a joke. Oh yeah, I have an A1. Yeah. OMG Frankie, I definitely have an A1. We're going to have to do something fun with that. Okay, so yes, what are lattices? I think it's probably going to be best if we just kind of read through this article from N-Topology. So what are lattice structures? Put simply, lattices are repeated patterns that fill a volume to conform to a surface. In engineering design, lattices are cellular materials, often inspired by nature, that consist of beams, surfaces, or plates that fit together in an ordered or stochastic pattern. So here you can see a couple examples of lattices. I like this graphic because it shows a lot of the different varieties of lattices. So here's our classic gyroid infill that we're all familiar with in 3D printing. This is a simple, like, repeated cubic lattice. But what's interesting here is they've actually varied the thickness of the lattice as you go along. So that's one of the interesting properties of lattices that I actually studied when I was in college, is you can vary the material properties of a lattice pretty easily as a function of, position or how much stress is going through the part. You can like just tell it to be thicker in areas where there's higher stress. So there's a lot of really interesting applications there. But you can go from a really thick structure to a relatively thin structure, all in the same kind of CAD representation. Then over here we have essentially a two-dimensional mesh that's extruded out into a lattice. And you can kind of think of this as it's kind of like corrugated cardboard. And in fact, this honeycomb structure is used in a lot of advanced composites applications. So, you can get 2 sheets of carbon fiber and then have a honeycomb fabric on the inside to bridge the gap in between the 2 pieces of carbon fiber, and then kind of shape it that way. And you can end up with really strong and lightweight parts like that. And then over here we have a lattice that's much less structured. This last one on the side, this is most likely a Voronoi generated lattice. So in nature, you would see this if you made a gigantic puddle of bubbles. Have you ever made a bunch of bubbles and looked at them? I don't know if that, like, you have a beer or something and there's all the bubbles at the top. Or you have a dish of soap and you blow a bunch of bubbles into it, or milk or whatever. These are Voronoi patterns, and Voronois are like a special type of lattice that's generated with a specific algorithm. I have a really interesting paper here. I've read this paper like 100 times because it's so good. And this is talking about procedural Voronoi foams for additive manufacturing. And basically the way these Voronoi patterns are generated is you seed either a 2-dimensional or 3-dimensional space with a bunch of points. You just put a bunch of dots down. And then you create a bubble at each one of those dots, and you grow it until it intersects with the neighboring bubbles. So there's a really, this is a well-studied algorithm. They use it in computer graphics and all sorts of, applications, and you can use it to generate 3-dimensional models. So here you can see their approach where they create these seed points, and then they find the intersections between these seeds, and they're all equidistant. So on this line here is equally spaced between this point and this point, and you can say the same thing about every single one of these lines. They're equidistant from all these pairs of points. So that's the Voronoi, edge generation technique. And the nice thing about it is it's just like an algorithm that you can implement, and then you can generate it. You can use it to fill any random space. It's just like a bunch of bubbles expanding inside of a volume. I think honeycomb would be a good shoe sole. The cubic would feel the best. Yeah. Cubic infill. Yeah, so let's look at this foam. This is definitely a repeating pattern. So I don't think it's a Voronoi foam. This is probably... you can actually manually generate these too. Like if you spend enough time in CAD, you can just extrude the pattern out and then do some Boolean operations to add it to the shape that you're working on, or do an intersect operation. So there's lots of ways to make shapes with lattices. End topology is kind of a unique CAD solution where they are building these lattices, and that's the main focus of the design software. It's not like SolidWorks where the intent is to make it into a solid object and then foamify it. It's like that's the intent from the get-go. Okay, and then there's some interesting stuff here. They've got volumetric lattices, surface lattices. There's stochastic lattices, and then beam-based lattices, and then repeating and honeycomb and all this kind of stuff. So there's a bunch of different lattices, and which one you use will depend on your application. So yeah. Let's see. Let's get back to our slideshow. So what are lattices? I guess according to the topology, it's any repeating structure used to fill a 2D or 3D space. And you know, any of those images would kind of work for describing that. All right, so let's get into the pros of lattice structures. So one, like there's a lot of pros and cons of lattice structures, and I've tried to go over them, but pro number one, reduce weight. That's usually the main thing that you're after, is like you've got a shape and then you're like, okay, this part needs to be this shape. How can I make it lighter? So reduced weight, more. The other pro is that it's compatible with additive manufacturing. So one of the reasons why we haven't used lattices all that much in the past is that we just didn't have the manufacturing capability to produce them. If you wanted to make a lattice like that out of a solid block of metal on a CNC machine, you'd end up having to do a lot of like machining and drilling out holes and stuff. But with additive manufacturing, you can just directly produce the lattices that you want. What are some other pros? Increased surface area. So this is if you're trying to do heat transfer, then having that increased surface area is going to be nice, just because it gives you more area to dump or transfer heat through. I guess 4 is it looks cool. So, I mean, that airless 3D printed basketball, I don't think people are really that interested in it for any other reason other than that it looks cool. So looking cool is important, and that's why you'll see this kind of stuff applied to like architecture and art applications. Good at absorbing energy. This is generally true of any type of foam. So, I mean, you can't see the individual cells of the foam in this slipper here, but it's squishy and it's made out of some kind of puffed up foam material. And the reason why we'll put it in shoes is so that it absorbs the impact of us walking on the ground. When you hit the ground, it'll squish a little bit and make it more comfortable. Let's see, what else do we got? I know there's a couple more. Anyone? Cool factor, yes. Ease of manufacturing, saves time. I mean, yeah, it reduces weight and material usage. A lot of the time when you're 3D printing something, the overall cost of the part is the amount of material that you use. And the amount of time that it takes to produce a part is also the amount of material that it uses. Versus in a traditional subtractive manufacturing process, you'll start with like a block of material and then you'll be machining things away. And actually it ends up that lightweight structures might take longer to build because you have to machine away more material. There's definitely a couple more. Oh yeah, this is a big one. So it allows multiple material properties on one part. So, I mean, I keep going back to this shoe example because I don't have a whole lot of other stuff within reaching distance that I can grab and show you. But, or maybe this hammer is a good example too. So with a hammer, you need something to be very tough and strong and heavy on the top, on the hammer head, but the handle doesn't need to be as strong or heavy or tough. So usually the way that you do this is you use two different materials. In this case, you're using wood on one piece and then metal on another piece, and then you're joining them together. But if you were 3D printing this, you could print the solid material for the handle. You could print the solid material for the head and then transition into a lattice for the rest of the part. So since you don't have to have it be as strong or heavy for the handle, you could just, start solid and switch over to your lattice here. And that could end up saving you in terms of part count or just simplicity of producing a product. What else? What else do we have? There's a lot of applications for this stuff with implants. So if you have bones, if you have like metal pieces inserted into your body, first of all, you need to use a material that's biocompatible. So usually they use titanium just because that tends to be pretty compatible with the human body. But also, you don't want the implant to be too hard or too soft. So if the implant is too soft, then you can imagine you put your weight on it and it crumbles. That'd be definitely a bad situation. But also you run into issues if the implant is too hard. So what'll happen is the implant will end up carrying all of the weight, and it'll cause other parts of your bone that it's inserted into to atrophy over time. So you want it to be the right amount of flexible where it can kind of squish a little bit and kind of stimulate bone growth where it's connected to the implant. So that's just kind of interesting. Is the arm cast the Prusa guy showed a lattice? Yeah, I would consider that a lattice. Anything that's not solid, I'd consider to be a lattice. But also in terms of biocompatibility, there's a lot of talk about people 3D printing organs. And usually what they'll do is they'll 3D print a lattice that's made out of collagen or something. And then they'll inject a bunch of cells that will kind of float around and randomly get stuck in random places inside of that lattice. And then they'll stimulate the growth and it'll fill out the organ. So then you'll get a biological 3D printed part. But that all relies on there being some kind of lattice structure with excess surface area and being made out of the right material. So they're useful in biocompatibility as well. And let's see. What are the cons of lattice structures? So increased complexity. Lattice structures are more complex just because there's more stuff going on than it just being a solid block of material. And the effects of this are larger file sizes. So, if you just have a cube represented as an STL, that's probably going to be a couple kilobytes, a really small file. But something like this represented as an STL, it has hundreds, if not millions, of little faces inside of this lattice structure. So, that could be an issue. A lot of these files take megabytes, gigabytes, even terabytes to represent because there's just so much data going on there. Yeah, 95% of general media showed about 3D printing is just showing some $1 million machine making a lattice engine looking part. That's definitely true. In a previous video, you incorporated a metal screen into layers of lattice. Yeah, so I mean, any type of sparse structure, any type of sparse repeating structure, you can consider as a type of lattice. And that's another interesting application that I put in the application section that hopefully we'll get to someday. Is that you can 3D print a lattice and then cast it into another object. I mean, think about like in conventional rebar construction for like rebar reinforced concrete. So here we're on Wikipedia. I mean, rebar is a type of lattice as well, because instead of using a solid metal beam, you're using a bunch of like small individual pieces that are strung together into a repeating pattern to fill up a space and add strength. So there's all types of lattices. Even I would consider like a crane. So cranes and bridges. These all use, you can actually see it right here. They use the word. This is a latticed boom. So this is a type of lattice. It's a repeating pattern to fill up the inside of the space to make this part larger while also keeping it light and strong and stiff. Like they could use a solid piece of metal for this, but then the crane would probably weigh like 1,000 tons, and that would be bad for obvious reasons. Well, for like practical reasons. So lattices are everywhere. I guess I'll show one more example, and that is, let's see. Well, the other thing to note is that even foams are considered lattices in my worldview. So this foam, this is a Voronoi foam. You see how it looks just like the computer-generated Voronoi foam? Like it's made using, I mean, this is a natural algorithm. Nature produces this using its kind of laws of physics. But yeah, all of these are lattices. And even at the micro scale, even at the microscopic scale, you can think of certain things as being lattices. So, for instance, precipitation hardening. Let's see if they have any pictures of this. No, they don't. Or, like carbon fiber reinforced plastic, or most people just refer to it as carbon fiber. Like these kind of parts, you have a lattice of carbon intertwined together and then kind of filled in with a matrix. They call it a matrix of epoxy. Bicycles are lattice structures. I wish there's a... So, I would consider a bicycle to be a trussed structure, but not necessarily a lattice. So a truss, you know, a trussed structure can be a lattice, but a lattice structure is often a trussed structure. I don't know. You get what I'm saying. It's like the squares, or a rectangle is a square, but whatever. Yeah, so trusses and lattices are pretty closely related. If it's a repeating pattern, then I would consider it a lattice. If it's just a single structure, then I would consider it a truss. But they are related, especially in terms of the way that we analyze them, in terms of like stress analysis and stuff. Okay, so pros and cons of lattice structures. We're on the cons section here. So give me some cons. I think I actually have a few listed. I'm kind of jumping ahead to my other section and stealing some of the points out of it because I think I brainstormed quite a few of the little ideas here. They can be more expensive. Thin lattices, the lattice structures themselves, if they're really small, they can be delicate, breakable features. There's sanitization issues. So when you add all that extra surface area, it's going to be more difficult to clean. You have limited material choices. I guess, yeah. Limited materials choices. Sometimes thin-walled or solid structures will perform better, and if that's the case, then you don't want to use a lattice. But yeah, I mean, back to like what is a lattice? What is a lattice structure? There's like naturally occurring lattices. I'll copy these images in. Like these soap bubbles. What else? I need to... Hold on. Okay. I'm just adding links here so I don't forget to later. So foams, these are naturally occurring lattices that you can produce, like, any type of foaming epoxy or like that stuff from Home Depot. The foam. This type of spray foam. This is producing like a small scale lattice. So I guess one thing I should delineate here is we can have large scale lattices. And these are like these are lattices that are usually constructed by hand, like out of individual beams. So let me just get a picture of that. So we've got our large scale. Medium scale. These are like your 3D printed features. Expanded mesh and those types of things. And then micro scale. So these will be like small cell foams where like you can't even... Oh, my camera. My camera gave up. I need to change a setting in my camera to keep that going. Hold on. Let me... There we go. All right, my camera should be going again. All right. So yeah, large scale lattices. These are things where you could like pick up the individual elements of the lattice. So like whether that's 2x4s or steel girders or whatever. You've got medium scale lattices, which are like 3D printed features, like 3D printed infill, expanded mesh, large cell foams. Let me look up expanded mesh or perforated mesh. Or like a basket. I don't know. Get creative with it. Whatever helps you remember it. Luke's lab. Yes. Lettuce structure. Green and crunchy. I haven't seen anything to do with resin and I know nothing about it, but I've seen mostly lattice structures displayed. Is resin useful? Engineer, I think I'll link this in my Patreon later. But this is not done yet, so I don't want anyone taking this and running with it before I thoroughly explain everyone to sleep. Yeah, so now you're getting into... Someone's talking about omnidirectional. So, yeah. Yeah, I wish there was a program that would calculate the geometry of strength into printed items instead of just base lattice menu selections. So, yeah, I do too. There's another foam... There's another paper that I think is really interesting. I'm not up to date on all the papers that have come out on this topic. But this one research group, HAL, I think it's based out of France. They have a lot of good research on like these lattices and how they can be used. So I'll show you. I actually did my own implementation of all of this stuff when I was doing research back in the day. And I've actually I'll show you something that I'm working on here. Here's something I'm working on. So I'm working on my own program to generate lattice structures. So I wrote something in Python and OpenSCAD for visualization. I'll probably get everything going in Python eventually so that I don't have to use two programs. But these are some lattices that I've generated, and it's fun to like play around with the rules on like when they should draw connections or when they shouldn't. And all of that's, all that's research and stuff. So this paper is called Orthotropic K-nearest Foams for Additive Manufacturing. And yeah, so instead of using a Voronoi pattern to produce the points, which is kind of what they're showing in this picture, they're using k-nearest foams. So you can see they're like varying the directionality of the foam. So it'll be stronger in certain directions. It's really interesting stuff. Yeah, I mean, I understand all of these plots. So if you want to do a deep dive into these, which I think I will do as a part of this lecture series, then let me know. But you can see like it adds a bunch of directionality to the foam. So one of the issues when you like hollow out a structure and turn it into a lattice is that the strength degrades rapidly. The strength and stiffness doesn't, like if you use 50% of the material, you end up with much less than 50% of the strength, which I can describe, which is described pretty accurately with like some functions that I can go over. Okay, so microscale, small cell foams, material microstructures. See, I don't know what they're looking at here, but it looks pretty interesting. Let's see if we can get some pictures of... Wow. I'm getting a little distracted here. This is a close-up of a Post-it note. Okay. A really common application of these electron microscopes is to look at the microstructure of metals. I guess they like looking at biological stuff too. I think all the flies and stuff look more interesting under the microscope, so they're not showing the pictures of metallography. Okay, sure. So you can see the yeah, we're getting a little off topic here. But I'm just having fun. Okay. Anyways. So yeah, large scale lattices, you can hold the individual pieces. These are just arbitrary definitions. Medium scale lattices are like tiny little things that you can see the individual components, but you know, they're not like microscopic, but you know, you can see the individual beams. And micro scale lattices are things that you have to use a microscope to see. So that'll be like, you know, really, really small structures. Usually these will be below the resolution of a 3D printer. Okay, so we talked about the pros of lattice structures, reduced weight and material usage, cons of lattice structures, and all right, relation to 3D printing. So let's pick back up here. Let me catch up with the comments here. So, oh my goodness gracious, you're actually doing it. So please, thank you. Yes, I am. I don't know how to program. If I did, I'd probably never leave the house. That looks amazing. Yeah, programming, it's not too hard once you get the basics of it down. I like having a programming interface to be able to produce the lattices because it gives you a lot more flexibility. There's actually a pretty good video from SolidWorks that I'll drop into probably one of these sections. But this video, I'll just link it here, and you can add it to your notes for later if you want to check that video out, or open it up in a new window. But in this video, they go over the process of modeling a basketball, and then they have this special package to be able to produce lattice structures. And it's sort of a programming interface. You can see they've got these blocks, and they have to feed the inputs and outputs together to produce a mesh, and then they produce a Voronoi pattern. You know, now that you know what a Voronoi mesh is, or a Voronoi pattern, you'll be able to recognize it when you see it. They're actually pretty commonly used in additive manufacturing. I actually don't think they're that good of a, it's not that good of a algorithm to produce a lattice, but it works, and it's pretty reliable. And I guess that's why people use it. Okay. I mean, I think the relation to 3D printing is pretty self-explanatory, so I'm going to delete this part. It would be pretty interesting to talk about the types of lattices. So, duplicate. And I'm just going to copy what N-Topology has here, because they have a really good overview of that. I mean, if you really want to learn more about this, this would be they have a lot of good resources here on their website. I mean, this is just a wonderful graphic. Whoever put this together gets kudos from me. Okay, so yeah, these are our lattice structures. All right, so the effect on material properties. I think that is, I mean, it sounds kind of boring, but it's really important. The whole reason why we have lattices is to modify the material properties of something. I mean, sometimes you add them just to make things more manufacturable. Reed Stevens, are you using any specific Python packages to get to do the visualized lattice project? In the past, I've used I think matplotlib. That's like a really common mathematics visualization library in Python. That's probably your best bet to get started. In this case, I was using I'm using OpenSCAD because it has a better user interface, and I believe you can export this to an STL and print it if you wanted to, but the export process looked like it was going to take a really long time, so I haven't successfully exported any of these larger lattices yet. But this is just more for my previewing. Like, I just want to see the data and see that all my points and lattices are being generated properly. So yeah, and I think this generates pretty quick. Yeah, this is under a second to visualize, to render this whole thing, for this visualization. Okay, so back to the topic at hand. So effect on material properties. This is where I think I'll talk about the how when you make something into a lattice, it loses strength rapidly. All right, so this is probably best demonstrated with a couple of graphs. And I know everybody loves graphs. So I'm going to draw one up here. This will just be, this is going to be terrible, but it's a pretty simple plot. I'll just do it by hand for now. All right, so insert text box. So I just made a simple plot here. On one axis is cable cross us. All right, cable linear density. And failure load. So that's like, hold on a second here. So if we look at this cable and we want to see how strong the cable is going to be or how stiff it is, basically the weight of the cable is proportional to the strength of the cable. So if we make the cable twice as thick, then it'll have 4 times the cross-sectional area, it'll weigh 4 times as much, and it'll be able to carry 4 times the load. So now I'll try to draw a graphic that demonstrates that. Cable double the area. All right, this is getting a little theoretical here, but bear with me. So All right, so here's our cable. Does this make sense? Let me know if this makes sense. So here's a cross section of the cable. All right. Does that make sense? So when I double the diameter of the cable, it gets 4 times heavier because for like a fixed length. I should add a note that it's a fixed length. I'm getting into slideshow mode. We'll do I guess a blue line. So we got a cable, it's a fixed length L, and if we double the cross section, it'll double the strength of it'll quadruple the cable. Does that follow? Am I going to Murph? Not 100% sure yet. Probably not. Oh, Murph. Maybe. Same answer, I guess. Yeah. Right. I mean, we could go through the math here, but basically, when you double the diameter of the cable, that'll make it 4 times stronger because you've got 4 times the cross-sectional area to spread that load out. And it'd also be 4 times heavier. So what you have here is a linear relationship between the linear density of the cable and the failure load, or modulus of elasticity. Now let's look at the same scenario. Hold on, density of cable. Now let's do the same thing, except we're going to be looking at a lattice instead. So all right, we'll delete that. And instead we'll add in a cube. So we're going to hold the size of this cube constant. But we're going to vary the density of the mesh of what it's made out of. We could also do this in a 2D scenario. So cross-section, yeah, proportional to strength. This would probably be a little easier to follow if I did it in 2D first, to kind of show the difference. Jumping straight to 3D. I'm gonna build this up as a hollow cube, which is gonna make everything really complicated. Yeah, this is gonna be rough, but if we can make it through this, it'll be good. Okay. So now we're looking at a cube. And if I want to make this a hollow cube, I need to do something. Doop. There we go. I'm going to get this to look a little bit better. Sun to back. Make it a little darker. There we go. Okay. So if we do the same experiment but with a cube, we end up with a different result. Let's go through it. Okay, so this is gonna take some math. It's gonna take some doing. So now let's look at the cube. All right, if we try and double the diameter of the lattice, of this lattice structure on the cube, and then measure how hard it is to pull that cube apart, we'll come up with something a little bit interesting. And 1 second, I need to plug in my fan to my need to plug in a fan over here before my camera overheats. Okay, this is where it gets tricky. And I might actually want to backtrack and just do this in 2 dimensions first. All right, so now we're doing the same thing with a 2-dimensional mesh. So instead of, just the single cable, we're going to have a mesh like this. Okay, so we're going to have a mesh. And instead of measuring the failure load of the cable, we're going to talk about like how much force it takes to pull this mesh apart. Okay, is anyone following? Anyone? Bueller? Okay, so yeah, let's just go through this. Now, we'll go through kind of the same math. I think I'll need to start a new sheet for this. Now, if we look at this in terms of, like, I want to pull this apart, we can think of this as 4 individual cables. In our previous case, it was just 1 cable, so it was pretty easy to do the calculations here. I'll add some of these red lines in so that we kind of have an analogy here. This red arrow indicates the force that's pulling the cable apart. Now when we have this 2-dimensional mesh, you'll notice that only and we break it into 4 individual cables here. Sorry, I'll just draw it up again. But I'm gonna make these top and bottom ones darker, because what you'll kind of see here is they're not load bearing. When you pull these, when you're trying to pull this apart, only these vertical beams are going to be carrying any load, and these ones that are running horizontally don't do anything, but they do add weight. So how do we come up with this? Let's assume that these are round cables, just like in the previous, or round beams, just like in the previous case. We want to double the diameter of the lattice elements, or lattice beams. This will still quadruple the weight, because the weight calculations are exactly the same times 4. But we're only going to double. Wait, yeah. Oh, hold on. Let's see. It'll quad. I hate doing this kind of math, but basically what we're going to see is if we double the diameter of the lattice beams, we'll quadruple the weight, we'll quadruple the strength. But the overall strength to weight ratio will be half of what it is for just an individual cable, because you've got twice as much material here. Well, this isn't making as much sense as I thought it would. Yes, all Safas. I'm trying to do it, and this isn't proceeding as well as I thought it would. Yeah, Reed, that's essentially what's going on, because you're adding weight in the direction that the load isn't being carried in. It might be better for me to just read what the paper has to say about this. Because you get, like, yeah. We'll get through this. And I think what you'd see if you extrapolated this out, what I'm going through doesn't really explain everything. But I think what you'd see if you extrapolated this out into 3 dimensions, is that you'd have even lower, like, failure load per weight. But I'm going to jump back into that paper and kind of show what they have to say about it. Because you get to a point... hold on, let me just bring to front. Yeah, okay. I think the point that I'm trying to make here is still valid, and that is as you create like a cubic mesh, it ends up not being as structurally efficient just because you have material in a direction that's not being loaded. So that's why sometimes the best solution is a simpler solution. Like in a suspension bridge, they have just cables holding things up. They don't need to fill that whole thing in with a cubic lattice because that'll be less structurally efficient, ultimately. So yeah, hopefully that point came across somewhat. But then there's another factor at play. That we'll talk about in a minute here. Okay. So yeah, I think I made the point that I was planning on making later with this. That you know, you want to get away with the lowest dimensional shape possible. If you can do the job with a cable, then do it with a cable. If you can do the job with a sheet of material, then do it with a sheet of material. You don't need to expand it out into a three-dimensional structure unless you're solving a problem that has to be solved in 3 dimensions. I think the other point that I wanted to talk about has more to do with well, let me just make sure that these numbers are accurate first. All right, so yeah, quadruple strength. Yeah. Oop. And then I think it's even worse in this case because now you're carrying the load on 4 of the beams, but you have 12 beams worth of weight. So it should be a third the strength of a cable. Yep. We'll call it good with that. I guess the other thing that I wanted to get into has to do with if you start with a cube of material and you start hollowing it out, you're barely reducing the weight at first, but you're greatly reducing the strength. And it kind of follows an exponential trajectory. All right, so this is the important plot right here. I just want to kind of introduce the idea that when you double something, when you double or half the amount of material that you're using, you're not necessarily doubling or halving the material properties. So like this kind of thing it's kind of non-linear. It's more of an exponential function. This is the kind of the most important equation of this paper, at least for me. This was my takeaway when I read this. Basically, if you half the volume fraction of your lattice, that is, you have, like if you have in one hand a solid block of material and in the other hand a block of material that weighs half as much, you're only about a quarter the strength of the solid material, just because of the way that like it carries stress within the lattice structure. So you end up with much lower strength to weight ratio. The way to combat this is to make the mesh directional. So kind of like in this other paper, these meshes with a high degree of directionality, where you can kind of see that they're kind of stretched in one direction. It'll maintain its strength in that direction a lot better, a lot more like in the cable scenario than when we're uniformly scaling the thickness of the beams up and down. Because you're not ending up wasting material on those sideways beams that aren't really carrying any load. All right, so yeah. I don't know how to describe that. It's sometimes I think about something in my head and it's like, oh yeah, that makes sense. And then I try to describe it to other people and I'm like, oh wow, I need to work on how I kind of vocalize how that works. But here we have some experimental data on, it's like they simulated a bunch of foam structures and then did some like finite element analysis on them and determined the material properties of the cube of foam. All right, well, I don't know. It's like skinny triangle structures in the direction of the load. Yeah, essentially. Or another way to think of it is you could make these the non-load carrying mesh parts a lot thinner than the ones that are actually carrying the load. So that would give some directional strength to this piece. One way to think about it is like a suspension bridge. It's essentially a lattice where they have the vertical beams that are load carrying, and they just completely set the diameter of the horizontal beams to 0. So like you can add directional strength into your lattices. Anyways, that was a very long and roundabout way of getting to this point, but yeah, that's kind of how I wanted to go about this. Just kind of go through my thought process on camera and see if we can come up with something that makes sense. I'm glad Reed gets it. I'm going to go ahead and drop that image. Of the suspension bridge. Where is it? Where'd it go? Nope, not that. It's one of these. There we go. Yeah. Anyways, it's weird. I don't know if it necessarily makes sense. What about foam, Ol? Oh, that's in Turkey. I thought that was the Golden Gate Bridge. But yeah, talking a little bit more about this two-dimensional analogy, when you make a material that's equally strong in both directions, it ends up with a lower strength to weight ratio if you're only loading it in one direction. Yeah, foam is a lattice structure. So one of the pictures I used earlier here is, where is it? Yeah, this foam. Yeah, foam is like a lattice structure that's assembled with basic physics instead of intentionally laying down each beam individually, like we do with 3D printing or in other constructed buildings. Constructed structures. Okay, so hopefully that got you thinking about things in terms of like, when I start trying to make things strong, if they're strong in all directions, then they end up, being overly heavy, and we can add some directional strength to stuff, and that way we can reduce the weight, and that'll make the strength to weight ratio better. There's analogies in this to like electrical flow. So if you have, there's just a lot to this. This probably isn't the best time to get into the deep dive without thoroughly planning out a lecture on the topic. Okay, so let's talk about the applications of lattice structures. So we kind of touched on this a little bit in the sneak peek, but maybe we can go into a little more detail here. One thing I'm really interested in, if you keep doing installments on the series, is specific lattice generation techniques like programming a Voronoi lattice or your improved directional version. Yeah, I think probably the best intro to that is, well, here's the problem. The existing CAD packages for doing lattice generation are extremely expensive. Like, I don't know how much N topology costs, or the SolidWorks equivalent, which is, I think it's called 3D Experience, and it's got like a plugin to all sorts of different stuff. I'm pretty sure this CAD package costs like $30,000 a year or something. You'd have to look it up. Yeah, so Logan, you're absolutely right, and that's what I was looking at. That's what they were investigating with this paper. So I'm a huge fan of SIMP, solid isotropic material with penalization function. It's a type of topology optimization. So here you can see they generate this principal stress field. So, all right, let me just explain what's going on with these figures, because I think they tell a pretty compelling story of how you can use these lattice generation techniques to produce optimal designs. So this is a boundary condition. This basically describes where the loads are and where the supports need to be for a given design. And this is usually how you'll describe a typical bridge problem. So let's say you can only build a support on this side and on this side, and let's say there is like a river in between these 2 points. So you can't build additional columns along there. And then you'll have a uniform load across the top here. So that'll be like your bridge platform that has its own weight and the additional weight of like cars and stuff. Yeah, so basically you want to produce a structure that's going to support this load and transfer all that load down into these support areas. And this is what you come up with using a topology optimization program. And yeah, it's simping. And then you can do some additional stress analysis on this design and see what direction the stresses are going inside of the part. And then you use that information to inform your lattice generation program. A, how dense do I need to make the material in a given area? And B, what direction should there be a preferential direction to the lattice that's being generated. So you can see here all of these little lattices are kind of having a preferential direction as well as a density. So it's varying the density. In this area in the middle, it doesn't really need much support, so it's like pretty sparse. But up here, it's like pretty dense. So yeah, I mean, really, the whole point of doing this is so that you can 3D print parts that are only as strong as they need to be. Is this paper using those 30K lattice generations? This is all being done using their own programming. They developed the algorithms to do this. I would like to get my hands on the algorithms and the code for this, because that would be fun to mess around with. But I ended up redoing my own implementation of this in another program. I was using MATLAB at the time. So yeah, I'd like to redo this in Python and be able to program my own stuff, because I've had some ideas that I think could be pretty interesting in terms of like doing these design things, solving these design problems in a fun way. Because I think CAD design should be fun. I think if you can make it fun and more engaging, then you'll be able to understand it a little bit better. Yeah, I don't know where the code is. Let's see if they have any mention of where the code is. No, they don't talk about the code as in Python. They don't talk about like the specifics of how they did this implementation. But if you want to learn more about SIMP, I'm a huge fan of SIMP. And you can actually download this tool to start playing around with it yourself. Let's see. So you can see you can build up these structures and add loads to it and see how the structure reacts. I'm going to make this a larger thing here and turn down the volume fraction. But this will build out like optimal shapes for supporting different loads. It's really fun. Like you can change the direction of the loads. And it'll automatically produce the optimal structure to support those loads. I like how it's very fluid. But if let's say you're an engineer and you need to design a bracket or something, which is basically all we ever do in mechanical engineering, we just design brackets over and over again. A tool like this can really help you come up with the best solution or the most lightweight solution for the problem. What do you guys think of this SIMP tool? I'll post a link to where you can download it. There's actually an app version you can get on your phone. This group's really good about like uploading their work and letting you play around with it. So the way that it works is if I pause it and reset it, um, you can see it starts out with everything as like a gray space, which basically they break this into pixels and they assign a density to each pixel. And then they do like a finite element analysis to see which pixels are carrying the most stress, and then it'll iterate through that. It'll be like, okay, these pixels have the most stress, so let's increase the density of this pixel and decrease the density of the rest of the pixels. And then it'll run the stress analysis again, and it'll be like, okay, this area still has too much stress and this area isn't stressed at all. So it'll continue to iterate through that over and over and over again until it comes up with an optimal design according to their objective function. And then you can actually export this to 3D print it if you want. I'm not sure if this actually works. You have to type in your email, and I guess they send it to you. Not sure if they're still doing that. Yeah. Yeah, I studied this algorithm pretty intently when I was in college. I think it's really cool. The main problem with these type of with this type of thing is it's hard to come up with the boundary conditions, or fully understanding what you need the program to do. But it'll come up with like really complicated shapes. And interpreting the results is like a whole thing on its own. All right, well, is there anything you guys want me to cover in more detail on the stuff we've gone into so far, or I don't know. This ended up being more challenging than I thought it would be, but it's always good to challenge yourself a little bit. My favorite thing to do is to produce a structure that's carries a moment like this. This ends up with the most fun-looking structure. This comes up, you get into the theoretical side of how to design structures, and you can end up with these solutions that people came up with like over 100 years ago, where they were purely mathematical solutions to the structural optimization problem. So you get these like really complex shapes. And these are like the optimal ways to support a load. This one's pretty interesting. This is this is what you see kind of like on a bicycle wheel. This is like a really common Prager trusses. William Prager. discrete Mitchell trusses. But yeah, you'll see this shape a lot. Even in this program, you can kind of see this shape emerging. There's this whole idea of like mesh dependence. So if you refine the mesh, like you give the computer more resolution to play with, it'll come up with a more complex solution, which I think is kind of interesting. Also, you can change the penalty function in this program, which basically the penalty function is what tells the program to not use intermediate values. The penalty function forces it to be either solid or void. But when you turn down the strength of the penalty function, it allows these intermediate kind of densities to be used, which are useful if you want to, like for this other paper where they were using foams, you actually want to turn the penalty function down, probably to about right here. Then you end up with like these foams only being used in kind of low stress areas. But yeah, that's about all I wanted to go over. I mean, this was just kind of a random topics kind of live stream. Hopefully everyone who watched it thought it was at least somewhat entertaining or interesting, or maybe you learned something. Yeah, I think I'm getting a little hungry, like I want to go get some lunch or something. But thanks everyone for joining. Also, big thanks to Star Guy, our patron saint, who has provided generous funding for this live stream. Okay, well, that's all I've got for now. Thanks for watching, everyone. I'll see you in the next episode.